Example 1, find the McLaurin series of the function f of x equals e to the power x and its radius of convergence. Solution: if f of x equals e to the power x, then the nth derivative of f of x equals e to the power x. So the nth derivative of f of 0 equals e to the power 0 equals 1 for all n. Therefore, the Taylor series of f at 0, that is the McLaurin series, the sum from n equals 0 to infinity of f, the nth derivative of f of 0 over n factorial times x to the power n equals the sum as n equals 0 to infinity of x to the power n over n factorial equals 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus ellipsis. To find the radius of convergence, we let a sub n equal x to the power n over n factorial. Then the absolute value of a sub n plus 1 over a sub n equals the absolute value of x to the power n plus 1 over open n plus 1 close factorial times n factorial over x to the power n equals the absolute value of x over n plus 1 approaches 0 is less than 1. So by the ratio test, the series converges for all x, and the radius of convergence is big R equals infinity. The conclusion we can draw from theorem 5 and example 1 is that if e to the power x has a power series expansion at 0, then e to the power x equals the sum from n equals 0 to infinity of x to the power n over n factorial. So how can we determine whether e to the power x does have a power series representation? Let's investigate the more general question: under what circumstances is a function equal to the sum of its Taylor series? In other words, if f has derivatives of all orders, when is it true that f of x equals the sum from n equals 0 to infinity of the nth derivative of f of a over n factorial times open x minus a close to the power n? As with any convergent series, this means that f of x is the limit of the sequence of partial sums. In the case of the Taylor series, the partial sums are big T sub n of x equals the sum from I equals 0 to n times the ith derivative of f of a over I factorial times open x minus a close to the power I equals f of a plus f prime of a, or the first derivative of f of a over 1 factorial plus, times open x minus a close plus the second derivative of f of a over 2 factorial times open x minus a close squared plus ellipsis plus the nth derivative of f of a over n factorial times open x minus a close to the power n. Notice that big T sub n is a polynomial of degree n called the nth degree Taylor polynomial of f at a. For instance, the exponential function f of x equals e to the power x. The result of example 1 shows that the Taylor polynomials at 0, or McLaurin polynomials with n equals 1, 2, and 3 are big T sub 1 of x equals 1 plus x, big T sub 2 of x equals 1 plus x squared over 2 factorial, and big T sub 3 of x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial. The graphs of the exponential function and these three Taylor polynomials are drawn in figure 1. See figure 1. As n increases, big T sub n of x appears to approach e to the power x in figure 1. This suggests that e to the power x is equal to the sum of its Taylor series. Back to the text. In general, f of x is the sum of its Taylor series if f of x equals the limit as n approaches infinity of big T sub n of x. If we let big R sub n of x equal f of x minus big T sub n of x, so that f of x equals big T sub n of x plus big R sub n of x, then big R sub n of x is called the remainder of the Taylor series. If we can somehow show that the limit as n approaches infinity of big R sub n of x equals 0, then it follows that the limit as n approaches infinity of big T sub n of x equals the limit as n approaches infinity of open bracket f of x minus big R sub n of x close bracket equals f of x minus the limit as n approaches infinity of big R sub n of x equals f of x. We have therefore proved the following theorem. Theorem 8. If f of x equals big T sub n of x plus big R sub n of x, where big T sub n is the nth degree Taylor polynomial of f at a, and the limit as n approaches infinity of big R sub n of x equals 0 for the absolute value of x minus a less than 0, less than r, then f is equal to the sum of its Taylor series on the interval the absolute value of x minus a less than r. And trying to show that limit as n approaches infinity of big R sub n of x equals 0 for a specific function f, we usually use the following theorem. Theorem 9, Taylor's inequality. If the absolute value of the nth plus 1 degree derivative of f, starting Taylor's inequality, if the absolute value of the n plus 1 degree of or derivative of f at x is less than or equal to big M for the absolute value of x minus a less than or equal to d, then the remainder big R sub n of x of the Taylor series satisfies the inequality. The absolute value of big R sub n of x is less than or equal to big M over open n plus 1 close factorial times the absolute value of x minus a to the power n plus 1 for the absolute value of x minus a is less than or equal to d. To see why this is true for n equals 1, we assume that the absolute value of the second derivative of f of x is less than big M, In particular, we have f double prime of x is less than or equal to big M. So for a less than or equal to x, which is less than or equal to a plus d, we have the integral from a to x of the second derivative of f of t dt is less than or equal to the integral of from a to x of big M dt. The antiderivative of the second derivative of f is the first derivative of f. So by part 2 of the fundamental theorem of calculus, we have f prime of x minus f prime of a is less than or equal to big M open x minus a close, or the first derivative of f of x is less than or equal to the first derivative of f of a plus big M open x minus a close. Thus, the integral from a to x of the first derivative of f at t dt is less than or equal to the integral from a to x of open bracket the first derivative of f at a plus big M open t minus a close bracket dt. F of x minus f of a less than or equal to the first derivative of f of a times open x minus a close plus big M times open x minus a close to the power 2 over 2. F of x minus f of a minus the first derivative of f of a times open x minus a close is less than or equal to big M over 2 times open x minus a close to the power 2. But big R sub 1 of x equals f of x minus big T sub 1 of x equals f of x minus f of a minus the first derivative of f of a times open x minus a close. So big R sub 1 of x is less than or equal to big M over 2 times open x minus a close to the power 2. A similar argument using f double prime of x is greater than or equal to negative M, negative big M, shows that big R sub 1 of x is greater than or equal to negative big M over 2 times open x minus a close to the power 2. So the absolute value of big R sub 1 of x is less than or equal to big M over 2 times the absolute value of x minus a to the power 2. Although we have assumed that x is greater than a, similar calculations show that this inequality is true for x is less than a. This proves Taylor's inequality for the case where n equals 1. The result for any n is proved in a similar way by integrating n plus 1 times. See exercise 83 for the case n equals 2. See the sidebar. Formulas for the Taylor remainder term as alternatives to Taylor's inequality. We have the following formulas for the remainder term. If the n plus 1 derivative of f is continuous on an interval big I and x is approximate and x is the element of big I, then big R sub n of x equals 1 over n factorial times the integral from a to x of open x minus t closed to the power n times the n plus 1 derivative of f of t dt. This is called the integral form of the remainder term. Another formula called Lagrange's form of the remainder term states that there is a number z between x and a such that big R sub n of x equals the n plus 1 derivative of f of z over open n plus 1 close factorial times open x minus a close to the power n plus 1. This version is an extension of the mean value theorem, which is the case n equals 0. Proofs of these formulas together with discussions of how to use them to solve the examples of section 11.10 and 11.11 are given on the website stewartcalculus.com. Click under additional topics and then formulas for the remainder term in Taylor series. Back to the text. Note, in section 11.11 we will explore the use of Taylor's inequality in approximating functions. Our immediate use of it is in conjunction with theorem 8. In applying theorems 8 and 9, it is often helpful to make use of the following facts. The limit as n approaches infinity of x sub n over n factorial equals 0 for every real number. Again, formula 10 or theorem 10 states that the limit as n approaches infinity of x to the power n over n factorial equals 0 for every real x. This is true because we know from example 1 that the series from the sum of x to the power n over n factorial converges for all x, and so its nth term approaches 0.